Section 2.5 is about the chain rule, and let's go ahead and start with page 1. So what happens is the chain rule is a differentiation function, but specifically it allows us to take a derivative of a composition or a composite function, which you can also think of as a nested function. So the rule is if both f and g are differentiable functions and y can be stated as a function of f, but f is a function of g, then the derivative of y is to just take the derivative of the f function with its inner piece as is, but then you need to take the derivative of that inner function, so in our case, g prime of x. Think of it this way. You're taking the derivative of the outer function, where at first you're just leaving that inner function alone, but this derivative is then multiplied by the derivative of that inner layer. So think of it as really kind of peeling off layers from the outside in. Let's take a look at this first example. F of x equals the square root of 3x plus 1, and I'm asked to find the derivative. So hopefully you recognize that the square root can be rewritten as something to the 1/2 power. So this is my outer layer. I have a function to the 1/2 power, but this inner layer, which I've written in green, is the binomial 3x plus 1. So according to the formula, I'm going to take the derivative of the outer layer. I'm going to think of having an exponent of 1/2, where my derivative, so I'm using the derivative notation, brings my exponent out front. When I subtract 1 from 1/2, I get negative 1/2. But notice I'm leaving this inner function alone. But now I need to take a derivative of that inner function. I can't ignore the 3x plus 1, and I went to a lot of detail here showing the derivative, but basically it just becomes 3. So now what I need to do is bring all of these pieces together. I've got a 2 in my denominator. My negative 1/2 exponent brings the binomial to the denominator with a positive 1/2 exponent. And since 3 was technically 3 over 1, I'm going to multiply the 1 and the 3 to just get a 3. Let's continue this. I'm asked to differentiate y, and I see y as the sign of a trinomial. The first thing I see is the sign, so this is the outer function. It's outside of the parentheses. I want to take the derivative of sine, which is cosine. Remember, I leave the original inner function alone, but now I'm going to take the derivative of that inner function. So the derivative of x to the 5th is 5x to the 4th. The derivative of minus 7x squared is negative 14x. And the derivative of a constant is 0, so you see nothing there. Now, in terms of simplifying this, you need to recognize that it's the cosine of a trinomial, and then that whole thing is multiplied with this binomial. So we do tend to write the binomial first so that it doesn't look like it's the cosine of a product. It's more clear that this is the cosine of a trinomial. And leaving these parentheses is crucial because it's not just the negative 14x. It's multiplied with the cosine. It's the entire binomial, and the parentheses indicate this. A couple more examples, and we're not going to simplify just because we're concentrating on the big picture. I see a trinomial, but I see it to a power. That kind of locks this trinomial parenthesis set. So I'm focused on the derivative of something to the 7th power is to bring 7 out front, subtract 1 from 7 to get 6, and then copy that original, in this case, interior trinomial as is. But now I'm going to take the derivative of x squared to get 2x. I'm going to take the derivative of plus 3x to just get a plus 3. And again, the derivative of a constant is 0, so we're not going to say plus 0. Now, I'm going to go ahead and move that binomial out front. We already had the 7 here, and because it said do not simplify, I'm going to just leave the 7 as is. I'm not going to distribute it. Keep in mind, the trinomial is to the 6th power. So we can never distribute into any parenthesis set that has an exponent beyond 1 because it's kind of locked, if you want to think of it that way. Next example, sometimes people don't always catch the best way to solve this. I'm taking the derivative of the x variable. The x variable only shows up once in the denominator, so I don't need a quotient rule, even though this may look like a giant fraction. I'm going to take this entire denominator and rewrite it with a negative exponent, and because it was a square root, which is the 1/2 power, we went ahead and made it the negative 1/2 power. So I'm just treating the 7 as a lead coefficient that I will bring back later. I'm focused on, I have a function to the negative 1/2 power. So I'm going to bring that negative 1/2 out front. I'm going to subtract 1 from a half in the form of denominator over denominator, which will give me negative 3/2. And everything that was inside the parenthesis stays untouched. Until now, I'm ready to take that derivative of the inner piece. So when I see the sign of 2x to the 4th, I focus on a sine function whose derivative is a cosine, where the interior is untouched. But in this case, I have one more layer because my derivative of the inside had its own inside. I have another inner function that I need to take the derivative of. The derivative of 2x to the 4th is 8x cubed. And in this case, let's look at all the pieces. So I've got a 7. I've got a negative 1/2. Because of the negative exponent, I'm going to bring that to the denominator. Whoops, and this says negative 2, but that should actually say negative 3/2. My cosine of 2x to the 4th is technically over 1 if you want to write it that way. And same thing, my 8x cubed is technically over 1. These double underlined terms all can be simplified together. The 7 times the 1/2 times the 8x cubed, where I can simplify to take half of 8, which is 4. So I've got the negative 1 times 7 times 4 for negative 28, and my x cubed stays there. So I'm going to bring this value over here and multiply it in front of my cosine x to the 4th. And then the mistake here where I had a 2, I did correct to be the positive 3/2.